Angular momentum for a particle. So let's take Newton's second law, where in the last video, remember, we said F equals d dt of mv, right? So force is equal to the rate of change of linear momentum. This product m times v is linear momentum. And if we have a constant mass system, we can take m outside of this derivative. d dt of v is just a. And so we get the F equals ma that everyone's familiar with. So again, mv is known as linear momentum, and we'll denote that as p. P, it's a vector, right? It's m times v. P is our linear momentum. And v is the absolute velocity, with respect to an inertial point. That's what absolute velocity means. So we can end up writing, F equals ma as F equals d dt of p, or d dt of m times v. It's all the same thing. So I drew this diagram here on the right, and this is kind of how we're going to think of setting up the problems when we get to some example problems, right? So we'll have some point O, and this will be our inertially fixed point. Then we'll have point A over here, and this is going to be the point that we want to take the angular momentum with respect to, right? So we're taking the angular momentum with respect to point A. And then we have point P, which is our point mass, our point of interest that we're taking the angular momentum of, right? So this vector pointing from our inertially fixed point to our point mass, this is vector RP. Pointing from O to our point A, that is RA. And then pointing from our point A to point P, that is just R. That's R. And if you recall your vector addition and subtraction, if you go from A to P, that's equal to RP minus RA. Gives you this vector right here, R, right? And that's written right here. R is equal to RP minus RA. Okay, so that's the setup. And there are two definitions of angular momentum that we're going to be using. Mostly it's going to be this absolute definition. So let's go over this one first. This is the definition of angular momentum with respect to point A. With respect to point A. And it's written as R crossed with P. So R, remember, is from A to P. And then P is this right here, M times V. And we can rewrite this if, we expand this P. It will be R crossed with M times RP dot, right? Because the derivative of RP, that would be our absolute velocity of point P, because it's taken with respect to this inertial point O. And then we can take this definition of angular momentum and take its derivative. So all we're going to do is take this, plug it in right here to our derivative, and then we're going to do the product rule. So derivative of the first times the second plus the first times the derivative of the second. Now what we notice here is we have this m times r double dot p. R double dot p is the absolute acceleration of point P. So this is ma, which is just F, right? That's our force. Here, force equals ma, right? So that's the force at point P. And then this R is the vector pointing from A to P. So this is R crossed with F. That's a moment. That's what a moment is. A moment is R crossed with F, and we're taking it with respect to A. So this is the moment about A of our point P. And then that's it. That's it. So this is the time rate of change of our angular momentum with respect to A. Okay, so we have these two equations, and what we end up doing in a lot of these problems is kind of think of these as two separate steps, right? This is our first step, and then this is our second step. So our first step, what we'll do is, we'll plug in with the appropriate vectors, and we'll solve for the velocity, and we'll get the angular momentum with respect to point A. We'll then take the derivative of this first equation, and that will give us some, HA dot, right? We're just going to take the derivative of this, and that'll give us some HA dot. So we have our first HA dot equation, right? And then we plug into the second equation, right? And we'll end up with a second, HA dot equation. So we'll have an HA dot equation from here, and then we'll have an HA dot equation from here. And then what we do is we set this equal to this. We set these two definitions of HA dot equal to each other, and that will end up giving us like our equation of motion, or it'll be a step in finding the equation of motion. But so that's usually the process we go about when we take this angular momentum approach. All right, the second definition is we have this relative definition. And, the relative definition and the absolute definition, they're going to both give you the correct answer. They're going to be the same thing, but sometimes it's beneficial to use one over the other. It could be less steps. Usually I just use this absolute definition. I think it's a little easier. But for completeness, I'm going to go over this relative definition. I have our little diagram redrawn up here on the top right. So the relative definition is, HA, our angular momentum with respect to point A, is equal to R, remember that points from A to P, crossed with M times RP dot minus RA dot. RP dot minus RA dot, well, that's just R dot, right? Because if we look here, R dot is equal to RP minus RA, so that means R dot is equal to RP dot minus RA dot, right? We just take the derivative of both sides. We're going to do the same thing. We're going to take the derivative of this first equation, right? And we're just going to take this and plug it into our derivative down here. And product rule again. So derivative of the first times the second plus the first times the derivative of the second. The derivative of this here is just RP double dot minus RA double dot. This right here, RP dot minus RA dot, that's R dot, right? We already said that. That's R dot. If you have a vector R dot crossed with itself, R dot, a vector crossed with itself is 0. So this whole term is just 0. And then we end up with just this over here. So we get R crossed with M, RP double dot right here, right? We just distribute this cross. And then minus R crossed with M, RA double dot. And we just said, using the same logic from the absolute definition, that this is the moment about point A. That's MA. So our final definition for the rate of change of angular momentum with respect to point A, using the relative definition, is the moment about point A minus R crossed with M, RA double dot. Okay, and again, we would do the exact same process that I outlined above, right? Think of these as like two separate steps, right? This is your first equation we're going to deal with, and then we're going to have a second equation here. So with our first equation, we'll find HA, and then we'll take the derivative of that, and that'll give us HA dot. Once we have HA dot, we can solve for this second equation just by plugging in, and then we set these two here, we set those two equal to each other, and that will give us our equation of motion. Okay, that's it. That's the end of this set of notes. If it's a little confusing, it becomes a lot clearer when we actually do an example. It's as easy as just like plugging in with these equations and taking some derivatives. So we're going to do a pendulum example next, so go watch that video. That's the end of this one. Bye.